Our next speaker is Professor Robert Marks from the University of Washington, Seattle. His talk is on the mathematical foundation of supervised neural nets.
Greetings. My presentation is in the area of artificial neural networks and supervised learning. It turns out that supervised learning, specifically the multi-layered perceptron, is by far the most widely used of the neural networks. Indeed, I would say probably 80 to 90% of the applications. There's been a lot of popularization of artificial neural networks and a lot of hype concerning them. We're going to look at the most commonly used models, motivated, of course, by our fact that we know that in some ways neural networks do work. Our motivation for looking at neural networks is somewhat like that of the Wright brothers. They knew that indeed heavier than air machine flying was possible, and we know that neural networks work because we have proof between our ears. So we do have that motivation. We're far from it, but we have developed from the neural models some very useful engineering sort of applications. I wanted to offer you my name and address and also my email, marks@ee.washington.edu, so that if any time that you had any questions or you wanted to follow up on any of this material, you'll be free to contact me. Supervised learning. In supervised learning, we are given a stimulus and an output response, and what we'd like to do is we'd like to learn the mechanism by which the input of the stimulus gives rise to the output. The object is to train a machine to be able to do that. Now, there are different approaches to doing that. One is the classical AI approach, artificial intelligence approach. In classical artificial intelligence, the manner in which these machines are trained, the manner is one of heuristics, of attempting to define the input-output relationship by rules. For example, in classical artificial intelligence, if I was to attempt to distinguish between a bush and a tree, I would give the artificial intelligence algorithm rules by which they could follow categorizing a bush and a tree. I would, for example, tell it that a bush was a small, squatty object and a tree was a very much larger object. In supervised training in artificial neural networks, however, the material is data-driven. The mechanism is data-driven to train the classifier, this thing that is to learn the input-output relationship. Specifically, instead of giving examples, we would give the neural network a bush, show it a picture of a bush, say this is a bush, show it another bush, say this is a bush, show it a tree, say it was a tree, and etc. And then after a while, the neural network hopefully would begin to be able to recognize a bush and a tree without giving it any additional information concerning the rules or the characteristics. The neural network will then emulate a classifier which is able to distinguish bushes from trees. The important part is if you show it, for example, a tree after the neural network is trained, the neural network will say, yes, it's a tree, but the important thing is that tree, whatever it is, cannot have been used in the training of the neural network. In other words, it's able to recognize things outside of the training data set. Now, the example that I just gave you was one of classification. The output is binary. It's either a bush or a tree. There's specific examples. There are other cases where neural networks can be trained to recognize continuous value outputs. One of the most commonly used in the area of power engineering is training a neural network to forecast loads. Here, the output of a neural network is an actual number, say between 0 and 1. And that number between 0 and 1, the continuous value, is associated on a table with the amount of load which is being forecasted. In a similar fashion, neural networks can be trained to emulate systems. You can give it a very complicated system, give it its input and the corresponding output stimulus, and the neural network is able to learn the input-output relationship. It it's kind of like, well, there was an old movie called Invasion of the Body Snatchers. And in Invasion of the Body Snatchers, there were pods which came down and they lied next to human beings, and they were able to replicate those human beings and act like the human beings. In a way, that's what artificial neural networks can do. They can be exposed, to example, to a system, and by having exposure to the input-output relationship of the system, they can be trained to have that same input-output relationship and therefore be able to emulate the systems. Let me give you a simple example of a classifier-trained neural network. This would be, again, a neural network. This is pictures of me and some other people. And there are two stages in training an artificial neural network. There is the training and then the testing. You need to train the neural network, and then after it's trained, you use the neural network to perform your classification. In this training phase that we have here, first of all, we expose a picture of me, and we tell the neural network or the classifier that, yes, this is Marx. We give it another picture and say, no, this is not Marx. Another picture, we say, this is not Marx. Another picture, we say, this is not Marx. Another picture, we say it's Marx, and another one which is not Marx. And we give it a number of examples, and then hopefully, after a while, the neural network is able to distinguish between a Marx and not a Marx. And then, if we give it a picture that it has not ever seen before, it will be able to look at this picture, run it through the classifier in this recall dimension of the neural network, put it through the classifier, and the classifier will categorize this as a Marx. Please notice that this picture, the test image, this is the test image, did not appear in the training data set. This distinguishes the concept of learning versus memorization. If indeed the neural network or the classifier was only able to distinguish items which it had seen before, it would be memorizing. The fact that it is able to distinguish and recognize items that it hasn't seen before means that the neural network has learned. Let's look at this in some sort of mathematical sense. We can talk about the classifier in feature space. Let's go back to the example that we had before. Here, this is again a case of a classifier, and this could be, again, an artificial neural network or some other classifier. We have a number of examples in space which are hopefully satisfying a representation. I'm sorry, not a representation, but a concept. The concept is the truth. It turns out, for example, in this case, that in this white boundary, any dot or any vector corresponding to, say, pixels of the picture or whatever, that lies in this white region would be a Marx. We are trying to learn this white region, but we don't have access to the boundary. All that we have access to are points within the boundary and external to the boundary. So we have dots within the boundary, and we have dots outside of the boundary corresponding to Marx's and not Marx's. The neural network or classifier then attempts to learn this concept. The learning of the concept is referred to as the representation. Hopefully the representation will be very, very close to the concept. And indeed, as we get more and more examples, we would expect the representation to get closer and closer to the concept. Now, when I showed you the picture that was not in the training set, that was an example of test data, the green dot, which we have right here. You'll notice that if the concept has been learned successfully, then the test data, which is here, will also be classified successfully. Clearly, there will be, in certain cases, errors. If we have dots in these regions here, they will be improperly classified. But we always recognize, I guess, that we're going to make errors of some sort, so therefore decide to live with a little bit of error. Now, this is an example of a binary classifier. Specifically, the output is specifically in a category. We had the example of a bush and a tree. We had an example of a Marx and not a Marx. We also have the continuous values. I mentioned the load forecasting. And we can envision this as a neural network or a classifier that gives continuous values of the output. Here we have what we'll call supervised regression. And what supervised regression attempts to do is take the training data and to successfully interpolate among the training data in order to give a successful representation of the underlying data. The output data is continuous rather than discrete. An example is load forecasting. Now, how would we train from load forecasting? We train on examples. In load forecasting, where we're attempting to, say, forecast the load demand of a system tomorrow at noon, there's a number of factors that obviously enter in. There is the temperature, which is forecast tomorrow, the day of the week, whether, for example, whether it's a weekday or whether it's a weekend, whether it's a holiday or not, because clearly the load is going to be a function of whether or not it's a holiday. Well, this data exists very richly in the database, and we can go grab it. We go grab it and we train the neural network with input of temperatures, the current load, the day of the week, the holiday, etc. And the output is the next day's load. We have the luxury in the database that we look at to know what the load is going to be tomorrow at noon, for example. Once the neural network is trained, and if it is trained successfully, we can do a test on the data. We test the data by putting in the input, the forecasted temperatures, the current load, the day of the week, the holiday, etc. The same thing that we did for the input, and then the output should be tomorrow's load forecast. And those of you who have read papers in the area know that indeed this is something that can be successfully done very easily. The multi-layered perceptron is the most commonly used neural network for supervised learning. However, it is not the only thing, the only regression or classification machine that can be used and can be trained using supervised learning. Here are some other examples. Well, these are not examples, these are properties that we would like in a good classifier, and then I will give you some specific examples. One of the things that we would like is good accuracy outside of the training set. Specifically, once we train the classifier or the regression machine, we would like it to respond appropriately to data which it hasn't been trained with. Number two, we would like an explanation facility. An explanation facility is as follows. If something is classified as a Marx, maybe we would like to have a reason why it was classified a Marx. For example, we might like to go back and look at the features which were used in order to classify it. For the bush tree example, we might classify something as, say, a tree. We would like to maybe look at the classifier or the regression machine and figure out why it was classified a tree. An explanation facility would be a mechanism by which we could go into the classifier and say, it was classified as a tree because it was big. In other words, we know the reasons for the classification. Neural networks are not, well, initially were not good for doing that. It turns out some recent research in fuzzy systems and something called lap art and some other areas now allow explanation facilities to be drawn from neural networks. Neural networks have been touted as black boxes. They have an input, they have an output. What goes on inside is a big mystery. That is becoming less and less true. And explanation facilities allow us to examine what goes on inside the neural network and extract the reasons why these classifications were made. Another property of a good classifier regression machine is fast training. We would like to be able to train the neural network or whatever classifier we're talking about. We'd like to train it very, very quickly. Unfortunately, neural networks are notorious for training slowly. There's been a lot of work done on training algorithms and a lot of different ways of training the neural network, but it's still relatively slowly. In fact, most good classifiers and regression machines train slowly, unfortunately. And then fast testing. Once we have the neural network trained, we would like to be able to have it respond very, very quickly. If we give it an input, a stimulus, we want the output immediately. And so these are properties of good classifiers and regression machines. Here are some other classifiers and regression machines which are not neural networks, which deserve honorable mention. Classification and auto-regression trees. There's been a lot of work actually done on comparing the layered perceptron to classification and auto-regression trees, and it turns out the neural network beats it in every sense. Nearest neighbor lookup is another one. Say, for example, one has a big list of training data and one has test data coming in. Why couldn't you simply take the test data, compare it to each of the points in the training data input, find the one that's closest and say, hey, this test data is closest to this training data, so the result or the consequence must be exactly the same. That would be referred to as nearest neighbor lookup. Nearest neighbor lookup grows as the database. If you have a humongous database, it's going to take you a long time to do nearest neighbor lookup. Also, there turns out there is artifacts in the classification boundaries which occur with nearest neighbor lookup. However, it is a very powerful, albeit simple way to perform classification and regression. Neural networks have won a lot of favor in the area of classifiers and regression machines, and the most popular is the layered perceptron and its siblings. There is the fundamental layered perceptron, that's the one that we're going to talk about today, and then there are siblings, they're kind of offshoots of the neural network, which have basically the same idea. Dr. Powell's functional link neural network is an example. Other examples, as you can see on the list, include the recurrent perceptron or the recurrent neural network, cascade correlation neural networks, radial basis function neural networks, and there are a number of others. So there's a number of variations. Let's then talk about the specifics of the layered perceptron and the model of the neuron. Here we have what I'm going to refer to as a neuron. And neurons usually are denoted schematically by just a dot on the paper. But here we're taking that dot and kind of blowing it up. Every neuron has a state or a number which is associated with it. So we have a state which is associated with the neuron S. Now the state of that neuron is determined by the states of a number of other neurons. So over here we have some other neurons and their states. And each one of these states, again, corresponds to a simple scalar number like 1 or 3 or 4 or 7 associated with the neural network. Now, how is the state of this neuron determined? It is determined by the states of these other neurons and the weights, W1 through W5 here, which weight the interconnects and the effect of the weights upon the overall state. The first thing we do is perform the sum. The sum is obtained simply by summing the input states times each of the weights. This summation then is subjected to a nonlinearity, and we're going to call this nonlinearity a squashing function, although other nonlinearities can be used. So this sum is subjected to the squashing function, and the result is a state. And this state we'll call S, and that is the number which is associated with this neuron. Now this state can be used for a number of things. It can be used as an output, or it can be used as the state input for some other neural networks. In biology, the interconnects among neurons are called synapses, and the weight, W, is the weight or the effect of the firing state of one neuron upon the state of another neuron. With that, let's look at the squashing function. There was a function here which we said subjected the sum to a nonlinearity and resulted in a state. Here's a squashing function. It's called a squashing function because it takes the sum, whatever it is. The sum in general will go from -infinity to infinity, and it will take that sum, and whatever that number is, it'll squash it into the interval from 0 to 1. So if the sum is 1,000,000, then the state will be 1. And again, it's called a squashing function because it reduces that interval from -infinity to infinity from 0 to 1. So therefore, in this model, using this squashing function, all of the states are going, or all of the neurons are going to have states which lie between 0 and 1. A very commonly used squashing function is the sigmoid. The sigmoid is given by this expression. You'll notice the sigmoid is a half at the origin. It's 0 at -infinity, and then asymptotically goes to 1 up here. And the sigmoid is used quite a bit because it differentiates very nicely, and we'll see that very quickly. Okay, so we have the idea what a single neuron looks like, what happens with that single neuron, the fact that we have a summation coming in, subjected to a squashing function, and the result of that squashing function, or sigmoid nonlinearity, is the state or the number associated with the neural network, or the neuron. So. So let's take a look then at a layered perceptron. The layered perceptron consists of a number of neurons which are interconnected with the weights. Now you notice that each one of these interconnects or synapse has a weight, and each one has a different weight. So here we have the input. Now the input usually comes from the data that is to be used to train the neural network. This might be, for example, features from a bush, for example, or the pixels from a bush. And the output would either be a 1 or a 0 corresponding to whether it was a bush or not. So each one of these neurons then has a state. The input has a state equal to whatever the imposed input is. These states then are broadcast to each one of these neurons in accordance to the interconnect weights. And so each of these neurons in the so-called hidden layer now have a number or a state associated with them. Each one of these states or numbers then is broadcast to the output layer, and each one of the output layer neurons takes on a state or a value also. So that's the basic idea behind a layered perceptron. Now, the question is given a bunch of input data and a bunch of output data, say some pixels about a marks and whether it's a marks or not, the question is how to adjust the weights here so that given an input of a marks, it gives an appropriate output classification. Figuring out what weights there are is equivalent to training the neural network. So let's look at training then. With training, you are given a training data set. You have an input vector set. This might be, for example, pixels from the picture of a bush or a tree, and we will denote this by a vector. An I sub looks like an N there. And then we have a corresponding output or target vector. We would like, for example, I sub 1 corresponding to a tree to map to T sub 1 corresponding to an output of 1. We would like an input of a bush, maybe I2, to correspond to an output of 0, etc. So these are the values that we would like to impose on the input of the neural network and the output of the neural network, and then our task is to find the weights of the interconnects using training data to minimize the error in the test data. In other words, we would like to choose the weights so that given, we would like to minimize the weights so that given the data set, we minimize the difference between the output of the neural network, what we get, and the target, which is what we want. Let's look at the error. There's a number of ways to talk about error. The most common is simply a sum of squares sort of data. Here we have our input target set. We have our input vector set, output vector set. The inputs are denoted by I, the targets by T, and the output is the value that the neural network gives on the output. Again, the target is what you want, and the output is what you get. There is going to be an error associated between what you want and what you get, and we can denote this error by a summation of the difference between what we want and what we get. And then we sum up the squares of those and divide by a half. This is put here for math reasons because later we're going to differentiate it, and that 2 is going to eat up that 1/2. Now, let's look at this error. Although it isn't explicitly said, this error is a function of a number of things. The error is a function of the input data, the error is a function of the output data, and the error is a function of the weights. In general, the input data and the output data, or the training data collectively, is fixed. We know the input data, we know the output data. That's fixed. So really, the only variables that we have concerning the error that we're really interested in is the weights. The degree to which one neuron is connected to another neuron, and we would like to be able to adjust these weights to in some way minimize this error. Again, the error is a function of the fixed training and data sets and of the neural network weights. The training and test sets are fixed. We want to find the weights that minimize the error. This is just standard optimization. Now, there are a number of different ways to perform optimization. In fact, there's people that make their living in operations research minimizing or maximizing some sort of objective function, for example, in control. And these people have a number of different tools at their disposal. We're going to talk about error backpropagation, which is an extension of steepest descent. But there's also conjugate gradient descent. There are genetic algorithms, evolutionary sort of programs, random optimizations. There are a number of ways that one can take an objective function, in this case the error, and to minimize it. And I want to point that out because we're going to be talking about error backpropagation, but it is not the only way to do it. It turns out to be a very good way to do it and a very, very eloquent way of minimizing the error, but it is not the only way. We're up against an optimization sort of technique. Let's look at minimizing the error using steepest descent. This was basically the idea of Woodrow and Hoff. Here's the main idea. What we would like to do is as follows. We have the error here, and this error is a function of, say, x. Now, x in general is going to be the weights, and I've done this in a one-dimensional space. Generally, this is going to be very high-dimensional space, depending on how many weights there are. What we would like to do is we'd like to find x, or the weights, that minimize this error. So we would like to be right here, because right here is where all of the error is minimized. How do we do that? The idea of steepest descent is as follows. We're at a point, and what we would like to do in order to find this minimum is we would like to stick out our feet and see which way is downhill, because we know if we go downhill, hopefully there's a minimum waiting for us downhill. How do we go downhill? We go downhill by taking the derivative of the objective function, whatever the derivative of the objective function is, and taking the negative of it. And then we simply replace the old value by the new value minus a step downhill, and then we have a parameter eta, which is the so-called step size. Here's an example of, simple example of steepest descent, where we have the error is equal to a half x squared, and of course we know that that has a minimum at 0. The partial with respect to x is simply minus x. So minus x is always downhill when this is the error function. So according to steepest descent, our new value is equal to our old value minus some step size times the derivative in error, that's the step downhill, which is equal to this. And it turns out that if we look at this as a difference equation, this is x sub p, and this is x sub p plus 1. We have a nice difference equation. This is has a nice solution. The solution is given here. And you can see that indeed this difference equation, as p tends to infinity, does go to 0, doesn't it? It goes to 0 as long as 1 minus eta is less than 1. So as long as we take sufficiently small step sizes, indeed, this is going to go as p goes to infinity. This is going to go to 0. And indeed, we'll find that minimum that we wanted to find. Let's use this then in training the regular vanilla perceptron. This is not the layered perceptron. This is just the regular perceptron with no hidden layers. Here we have inputs, and we have corresponding outputs, and we have weights parameterized by how they connect the input to the output. W24, for example, connects input 4 to output 2. Okay, what is the error then? The error is equal to a half times the summation of the two output neurons of the difference between what we want and what we have. If we expand this and take the partial derivative of it, we find out that the derivative downhill can be expressed very nicely in terms of the current input and the error at the output. And it's very cute, eloquent math. It's in the tutorial book associated with this tutorial, and the math which I'm sharing with you is very nice and very eloquent, and I know it's something which can't be grabbed upon a first presentation, but we wanted to point it out, and then hopefully you'll take time to look at the math and absorb it very, very completely. So here's the weight update. Here is the derivative as we derived last time, and the update is very simple. The new weight is simply equal to the old weight minus a step size times I4 times the difference between the two. What is really cute about this is as follows. We're trying to update the weight between this input and this output. The weight between this input and this output is only determined by the value of the weight here, the value of the input here, and the value of the output here and the target here. Notice it's input 4 and the output 2 minus the target 2. So we can update this weight only knowing this input, the corresponding output, and the target there. We don't have to know what is going on anywhere else in the neural network. And that's really an eloquent solution. The updating can be done totally inside the neural network. There's a problem with that, though. This was basically the neural network that was looked at in the 50s and the 60s. The problem with it, though, is that with no hidden layers, you're kind of limited in the sort of data separations you can have. Let's look at that specifically. If the output is equal to the squashing function operating on the input, then we have the following situation for a classifier. For a classifier, if the output is equal to 0, if the output exceeds a half, we say the output is 1. If the output is less than a half, we say that we have a 0. So the output equal to a half is where the boundary is going to be between the two. Let's look then specifically at the case when the output is equal to a half. Now the output is equal to a half occurs when the summation of the weights times the input is equal to 0. Now what this says is that this is the defining boundary that is going to separate one class of data from the other class of data, and that the separation that we have between one class of data and another class of data always has to be a line, and it always has to be a line going through the origin. This is terrible, unless you have a linear separable problem. So if we had data like this, and we were trying to separate the green dots from the yellow dots, the perceptron with no hidden layers would work fine. We always have a line going through the origin, and what the neural network would do would essentially kind of search around and find out that, gee, this was the line that gave us minimum error, and if we were on this line, we would have 0 error. So let's use this line. Well, we can get away from that problem of a line going through the origin a little bit by introduction of a bias. And the bias is an important term. We're going to have the traditional inputs that I showed you, and we're going to have an additional input, which is always going to be 1. And it's always going to be 1. That might be troubling at first until you recognize that we can control the interconnect or the contribution of 1 to the overall output. What happens with the introduction of 1, it allows this line to go from the origin. It need no longer pass through the origin. So we can still do linearly separable problems. The challenge, of course, is still that we're limited to very special data. We're limited to data that is separated by a line. We would like to be more general than that. In a book, Perceptrons, written by Minsky and Papert, they explored the regular perceptron, and they said, look, I'm going to give you a really simple problem that this perceptron can't do, a very simple problem. And the fact that it can't do this problem means that it probably can't do a lot of other real-world problems. And that simple problem I'm going to ask you to do is a simple exclusive OR. So we'll call this the Minsky-Papert objection. Exclusive OR, we have zeros here and here because the exclusive OR of 1 and 1 is 0. Exclusive OR of 0 and 0 is 1. Here we have 0, 1, 1, 0, 1, 0, 1. So here we have 4 points, and we can talk about this as points being classified. These are points which are on the square. You'll notice that there is no way that we can get a line to separate the yellow points from the green points. And the point that Minsky and Papert were making is not that neural networks should do logic sort of operations. We're not really interested in doing that. There's a lot cheaper ways you could do it. But the fact that it can't do the exclusive OR means that there's probably a lot of real-world problems that are very, very simple that this perceptron with no hidden layers can't handle. And indeed, they're correct. They were correct in that observation. So therefore, we came and generated the layered perceptron. The layered perceptron, as we mentioned, has different layers, usually 1 or 2. More layers are possible if one so desires. But we have an input. We have the interconnects with the corresponding weights connecting them. Here we have 2 layers. We have the output neurons. and we provide an input and an output, and it turns out that the neural network here, when used for classification, can generate an arbitrarily large number of nonlinear sort of partition boundaries and classification results. And it is the use of the hidden layer that allows us to do that. We will quickly look at error backpropagation. I don't want to get bogged down in the math because that becomes very boring in presentations, but I will refer you to the tutorial book where the math is included and it's elaborated on. And again, please take a look at it. It's truly a work of art. And it works very practically also. Error backpropagation. For an arbitrary weight, we want to update according to steepest descent. The j-kth weight and the lth layer, we're getting pretty rich in notation here, the j-kth weight in the lth layer is replaced by the old weight minus a step size going downhill. That's what this derivative is. The essence of backpropagation is the expansion of the going downhill term, this partial, into separate terms using partial fraction expansions. The partial with respect to W is equal to the partial with respect to S times the partial of S with respect to the sum times the partial of the sum with respect to the weight. These kind of cancel out, and we're left with just the partial with E with respect to the weight. The beauty of this expansion is that each one of these individual terms in this expansion has a very eloquent interpretation. Let's first of all look at the first term here. That's the derivative of the state with respect to the input sum. Do you remember that we used as the squashing function that 1 over 1 plus e to the sum? And we said that that had very nice derivative properties. Well, here it is. It turns out that if we take the derivative with respect to the sum, we get the original function times 1 minus the function. Work out the math. Works very beautifully. So therefore, the derivative with respect to the sum in that previous term is very easy to evaluate. The derivative of the sum with respect to the weights is simply the state of the neuron. And we have one troublesome term here, which turns out not to be troublesome. It looks troublesome initially. The partial of the error with respect to the state. Now, this term appears so much, we're going to give it a special name. We're going to call it del sub j. The neat thing about del sub j is it can be expanded into a summation, and this summation is a function of other del sub j's. And what we'll find out is that this term can be determined from del sub j's from layers above the layer that we're examining. And the output layer del sub j's can be found very, very easily. Okay, here is the weight update then. The weight update expanded is equal to the del sub j's. We're going to say more about that. In fact, it's these terms that we get using backpropagation, times a function of the states, and these are the states of the neurons which are performing the connection. Let me go through graphically how we train then a neural network, a layered perceptron. This is a simple 2, 3, 2 neural network. The first thing we do is we supply the input from the training data. Using the weights and the squashing functions, we compute the states or the numbers associated with each other neuron in the neural networks. So this is the feed-forward dimension of the training. We're taking the input and we're sweeping it towards the output, and as we go up, we compute all of the states as we go up. Once we do that, and we're at the top, we have the outputs of the neural network. Now this isn't what we want, this is what we have. We know what we want the targets, we have the O's. So we can figure out the error, the difference between the targets and the outputs, and compute the error. And it turns out then that this error can be used to compute the del sub j's, these troublesome derivative terms at the output. And then these del sub j's in turn can be used to assign del sub j's to all of the other neurons. This is the reason we call it error backpropagation. In the first sweep, we go up and we color all the neurons. We give each of the neurons a state. Then we go back down and we give each one of the neurons a del sub j, a derivative term. So now each neuron has two numbers written on it, the state and the del sub j. So we have totally colored in the neural networks with the states and the del sub j's. Once we have that, it's simple to update and interconnect. We're going to look specifically at this interconnect and the weight update between I2 and this neuron. The weight that we're updating is W32. The new weight is simply equal to the old weight plus all of these terms. Now don't forget, each one of these neurons has a state associated with it and a del associated with it. And you'll notice that in order to update this weight, the only thing we need to know is the states and the dels here and the states and the dels here. So this weight is simply updated using steepest descent, using this formula, and one has to choose some sort of step size. And we can do that for each one of the neurons. The neuron here and here can be updated, the interconnect between this neuron and this neuron can be determined totally by the states and the deltas associated with the neurons that connect the weight. So the updating and the training of the neural network can be done totally inside the neural network. This is why error backpropagation is so eloquent and probably one of the reasons why it's so widely used. If you were to attempt to use any of the other optimization techniques, say conjugate gradient descent or random optimization, it would be more of a math problem. You would have to, if you will, kind of extract the parameters from the neural network, turn it in a machine and kind of crunch, and then out come the weights, and then you would have to impose the weights back on the architecture. Neural networks and backpropagation, as we have described them here, is a procedure whereby training can be done totally inside the neural network, totally within the structure, giving rise to all sorts of possibilities in parallel sort of processing. Well, this is a vanilla description of error backpropagation. We can talk about so-called neural smithing. It does turn out that error backpropagation is something that's easy to explain but more difficult to use. And in fact, use of error backpropagation in training neural networks is still somewhat of an art. And we can talk about so-called neural smiths who are practitioners and people that train neural networks a lot, and the little tricks and the little things that they use in order to train the neural network better. So let's take a look at some of the things we're going to touch on briefly. We'll talk about the idea of bias. We've already talked about the idea of bias with the perceptron with no layers. Talk about the use of momentum, batch training. We've talked about learning versus memorization. But we're going to revisit this in the layered perceptron to find out, hey, when have you successfully trained a layered perceptron? How do you know that you've learned and you haven't memorized? We do this through cross-validation. I will say some comments on the curse of dimensionality. And then, as we mentioned, there are a number of variations of the layered perceptron, and we'll touch on these just a little bit. Okay, first of all, bias. We saw that in the neural network that didn't have any hidden layers, that we needed a neural network, we needed a bias on the input to allow classification where the line didn't pass through the origin. In other words, what the bias did was give us an extra degree of flexibility in being able to categorize the data. Use of bias in layer perceptrons gives us similar sort of flexibility. We can apply bias both at the input layer and at hidden layers also, and allows, again, for greater flexibility. So the bias is used with a multi-layered perceptron at the input and sometimes at the hidden layers. Momentum. One of the things that somebody attempting backpropagation will immediately notice is it doesn't work most of the time. And the reason it doesn't is because downhill can be so incredibly erratic. What we would like to do is as follows. We would like to give that little ball that's going downhill, and each time it takes a little step, we'd like to give it momentum so that as it's going downhill, the next step is kind of in the same direction as the previous step. That going downhill doesn't have to be like this and this and this and jump all over the place. We'd like to give it a little bit of memory. And again, in physics, that is exactly what momentum is. Let's look and see how we do that. Steepest descent replaces the old value by the old value plus a value of eta times a change in the step size, and this is given by the parameters of the neural network. We can also add a momentum parameter, which gives the ball going down the hill a little bit of memory, a little bit of inertia, if you will, by adding a alpha on here, which is proportional to the previous weight change, so that the new weight change is computed newly, plus it's a little bit of the old weight change also. This gives the ball a little bit more of inertia and helps it find the minimum quite a bit better. What I explained to you in error back propagation is really not steepest descent, because what we have is as follows. We have let's take the bush and the tree. We have the bush input, and then we have the bush category. So what we do is we take all the weights and we update them according to whatever the error is. Then we have another input, and that input could have a totally different error surface than the previous input. Batch propagation training is actually true steepest descent, and it does the following. It takes all of the input data set and it puts it all in sequentially, and we don't update the weights every piece of data. We put the whole set of data in, and then we add up the error. We add up the error from all of the inputs. Then we use the summation of all of that error one time to backpropagate and update the weights. So therefore the weights are backpropagated in accordance to the entire data set or the entire batch of data every time. And this is true steepest descent. So the idea in backpropagation batch training is, again, to accumulate the error from all of the training data prior to the weight update. And we update weights each epoch. And each epoch means an epoch means a pass through the data. And so this is batch training, and it works a lot better. I mentioned previously that there's a problem, that we want to make sure that we learn and we don't memorize. How do we learn and not memorize? Let's talk about that a little bit. By learning, we want the neural network to classify or to give a result that is reasonable for data which is outside of the training set. We want it to be able to respond to things that it hasn't seen before. If it can only respond to things that it's seen before, then indeed that's simply memorization. And memorization is very easy to do. Let's look at a case where we might have memorized. We go back to our idea of having a concept and a representation. So here is before. We have in white, we have the concept. This is the truth. This is the boundary that we would like to learn. And the green boundary, we decided was a boundary that, hey, is pretty reasonable. It fits the concept pretty well. We could also have an other boundary. And this other boundary would, for example, be this big blotch of, looks like whitish or pink or something. And guess what? This big blotch successfully categorizes all of the input data. You'll notice all of the yellow dots here, all of the yellow dots lie within the big blob. And so, yes, indeed, it has memorized the training data very, very nicely. But you'll notice there's a problem. If we give it a training point or a test point right here, you see that little green dot, it's going to do a very, very bad job. If we give it this little green dot, it's going to do very, very bad. So, indeed, this is how we test whether the representation is close to the concept. We show the neural network data that it hasn't seen before. If it successfully categorizes it in most cases, then we say that the neural network is successfully trained. If, on the other hand, we give it data and it gives us a lot of erroneous examples outside the training set, here's a green one outside here, which would also categorize improperly. If it gives us a lot of problems, we know that we haven't trained it successfully, that the neural network has memorized. Here's another way of looking at it. If we were given a number of points on a line, here's a number of points. We'd like to be able to draw a curve through it. The representation here, the concept, which is the white line, which comes down here, is what we're trying to learn. You'll notice that the green line successfully passes through all those points and is pretty close to the white line. Whereas this other wildly varying curve is very, very far off and is a very bad representation. You'll notice that if we expose this to points which were outside the training data set, say this point on the white right here, you know that the representation which was close to it would categorize it pretty well. Yet this representation which is far away would categorize it here. So again, it's the case where we'd like to have the representation be close, and the way we do that is we test the neural network with data that it hasn't seen before. So here's what we'd like to do. would like to find out the difference between learning versus memorization. Successful learning recognizes data outside of the training set. For a neural network, this means the neural network must successfully classify or interpolate inputs it has not seen before. How can we assure learning? One is with cross-validation. That's simply the idea of, after training the neural network, we expose it to data that it hasn't seen before and make sure that the response to the neural network is appropriate. We also would like to choose the neural network structure properly. In a way, we're asking how many degrees of freedom is needed in order to characterize the data. Each different neuron is a different degree of freedom. It's a different degree of flexibility that we have in performing the classification. If we have too many neurons, we have too much flexibility. Chances are that the lines that we're going to use in classification are going to be very, very wiggly if we give it too much. If we give it too little, it doesn't have the freedom to get the classification boundaries exactly right. So also, good learning must take into account the number of neurons which are used and how many layers which are used. Here is a common way, once you've chosen the number of neurons and the number of layers, of determining when you quit training. We start training and we have the training error. This is the error that is available at the output of the neural network. We have a second bunch of data which we call the test data. We also test the test data and compute the error corresponding to its output. We do not use the test error, however, to update the neural network. When the test error bottoms out, that's the point where we should quit training the neural network. Because at this point, the neural network has learned all it can in the current configuration, and if we train it anymore, it's starting to memorize. The actual error on the test data is increasing, and that's something that we don't like to do. So one technique, there are many, to determine when to stop training is to monitor test error and stop when that test error minimizes. This again is a totally different database. It is not used to train the neural network. It is not used to update the tests and update the weights. Another aspect that needs to be taken into consideration in training a neural network is the curse of dimensionality. There is the tendency sometimes in training a neural network of saying, hey, let's just put everything that we can into the neural network and see what it does. It turns out that there is a good solid reason for limiting the dimension of the input layer. In other words, we would like to have, as a minimum, the number of inputs that we can have. I'm going to give you a quick explanation. The reason for it is something referred to as the curse of dimensionality. For many problems, the required number of training data increases to the power of the input's dimension. I'll explain exceptions to this very shortly. For n is equal to 2 inputs, suppose that 100 training data pairs are required. For n is equal to 3 inputs, it turns out 1,000 are required, and in general, if we had inputs, 10 to the nth training data points are needed. And this is the number of inputs. So you can see as the number of inputs increases, the number of training, the amount of training data increases and increases incredibly. Let me give you a justification for that very quickly. Here's a simple example of 2 inputs, I1 and I2. So here's I1 and I2, and a corresponding output. And what we would like to do is we would like to classify points within a circle as opposed to those outside of the circle, but still in the square. So we have I1, I2, so this result, this point, I1, I2, would be classified as a square. This yellow dot inside would be classified as a circle, etc. Now, shown here are 100 points. And this is a rough call. How many points would it take, randomly spaced, to recognize the difference between a circle and the square? And let's just say 100. Let's agree on that. I think more would be needed, but let's say 100. Let's extend that now to one more input. We now have 3 inputs. So now our circle becomes a sphere. Now, in essence, what we need to do is we need to classify a point within the sphere or within the box. So now we have simply added one more input. Before we had 2 inputs, now we have 3 inputs. Let's see what happens to the data. If we needed 100 for this circle, say here on this plane, would not we need 100 for each one of these slices, each one of these planes? The answer is yes. We would need 10 for each one of these planes. And so that would be 10 layers, each with, this is 10 layers of the slices here, not neural networks. So we have 10 slices here, each with 100 points. So that's 1,000 points. So in general, if we had n inputs here, we would have 10 to the n points. This is the curse of dimensionality, and is the reason that it's inadvisable to use neural networks with a large number of inputs, unless, of course, one has an incredible amount of training data that one can use. There are exceptions, of course, to the curse of dimensionality, and it is problem dependent. You could have, for example, training data which only existed on a manifold or some sort of curved space in your larger dimensional space. In those cases, the curse of dimensionality wouldn't hold. But I think you can see in this simple square to sphere example, the curse of dimensionality is very real, and the number of training samples increases incredibly. We're talking about neural smithing. And there are variations. Recurrent neural networks, we'll go over these very quickly. Recurrent neural networks are networks where there is feedback. There will be feedback from one neuron in one layer back, for example, to an input layer. So therefore, these are recursive or recurrent neural networks. And they are able to capture very long sequences in time using the memory, if you will, of a feedback, much like the difference between an FIR filter in digital signal processing being the feed-forward neural network, and the IIR, or infinite impulse response, being the kind of the recurrent neural network. It does have feedback. Radial basis functions use Gaussians instead of squashing functions as the nonlinearities, and have totally different functions. Cascade correlation is another one. Fuzzy multilayered perceptrons are very nice because they allow for an explanation facility. They are neural networks which are made in the form of fuzzy inference systems, and once the neural network is trained, the trained neural network can be looked at and rules extracted from it. One can look at a trained fuzzy perceptron, layered perceptron, and actually extract if-then rules from the trained neural network. If this input is such and such and this input is small, then the output is going to be such and such. So these do have the explanation facilities with them. These are some of the variations. There are numerous others which you can find in the literature. And also the training algorithms we have mentioned. Training a neural network is an optimization problem, and clearly there is more than steepest descent in the realm of optimization. Important dimension is in applications. And this will be the last topic that I touch upon, applications. In terms of applications, as mentioned in the beginning of the talk, probably 90% are concerning the layered perceptron. Now, by applications, I don't mean journal papers. I mean places where neural networks have found use in the field in an ongoing basis. There are numbers of applications in the area of power engineering. Other tapes in this series will address that. In the area of finance, we are seeing an explosion of interest in neural networks. People on Wall Street attempting to predict the market, for example. Turns out that's not a very smart thing to do using neural networks, but there's other very exciting areas in finance where neural networks are finding numerous applications. The area of bioengineering, the ability in pattern detection, for example, to detect and classify irregularities in biological signals, such as EKGs and EEGs. We're finding neural networks have a number of applications there. In the area of control, one of the tapes in this series deals with applications of neural networks to control. This has been a very successful application. In industrial applications, I'm from Seattle. Boeing uses neural networks online for a number of purposes, one of which is classification and categorization of tool parts from their silhouettes. They tried a number of different ways to do it and found that neural networks indeed did it the best. One place which you wouldn't expect it is in the area of politics. And there are some fascinating applications. 1996, Bill Clinton was running for the White House, and used neural networks in his re-election bid. This was in a column by Robert Novak. He appears on CNN, and he also does a syndicated column which appears in a number of different papers. This one appeared in February 1996. This is titled Undecided Bowlers. President Clinton's pollsters have identified the voters who will determine whether he will be elected to a second term. Two-parent families whose members bowl for recreation. Using a technique they call the neural network, Clinton advisors contend that these family bowlers are the quintessential undecided voters. Therefore, these are the people who must be targeted by the president. So we actually see the use of neural networks in politics. I am not familiar with the details of how exactly the neural network was trained, but I would like to find out someday. I wonder if it was with somebody with true experience. Novak continues, and this is interesting. He says, a footnote, 2 decades ago, Illinois Democratic Governor Dan Walker campaigned heavily in bowling alleys in the belief he would find swing voters there. Walker had national political ambitions, but ended up in federal prison. So we see that neural networks have a large number of applications, all the way from power engineering to the area of politics. And are very useful. 90% of the neural networks used today are layered perceptrons, ones that are used in the field. It's used in the vast majority of electrical engineering applications, and it does use supervised learning. Most of them are trained through error backpropagation. There's also been a number of papers and a number of studies done to improve error backpropagation. The most successful are variations called rprop and quickprop. Both are very nice accelerations on the use of backpropagation to train the artificial neural network. The question is, will the supervised learning and the layered perceptron maintain their dominance in the field? Probably for the near future, but hopefully we can study the brain and other areas in learning theory and be able to come up with even new and improved ways to perform these classification and regression problems using supervised learning. Thank you.